Today we are beginning chapter 10, which focuses on waves. In this chapter, help me, I've been trapped in the computer, please help me, 6-7, Skibbity Toilet. We will explore how energy moves through the material and space to form waves. We will learn what waves are, how they behave, and the different types of waves, and how to calculate important wave properties such as frequency, wavelength, and wave speed. Waves. A wave is a repeating disturbance or movement that transfers energy through matter or space. The images show ripples in water, colorful wave patterns representing energy moving through a medium. I actually had that as my desktop background when I was like 12. Example of waves. Examples of waves include ocean waves, earthquake waves traveling through the earth, and light waves traveling through space. All three we will talk about as the chapter progresses. Progresses. That's not a word. Close enough. How are waves formed? If you drop a rock in a pond, the rock transfers energy to the water and ripples to spread outward. Those ripples are carrying the energy away from the impact through waves. Energy. Waves transfer energy without transferring matter. A boat floating on water mostly moves up and down as waves pass beneath it rather than traveling with the wave. More about waves. All waves are produced by vibrations. The material a wave travels through is called a medium. Some waves, like light, do not require a medium and can travel through empty space. Mechanical waves require a medium to travel through. They come in two main types, transverse waves and compressional waves, also known as longitudinal waves. Transverse waves. In a transverse wave, matter moves at right angles to the direction the wave travels. Ocean waves are a common example. Water moves up and down as the energy moves horizontally. Now we will look at compressional waves, also known as longitudinal waves. In these waves, the particles move back and forth in the same direction that the wave travels, like a slinky. The diagram also shows a slinky being pushed forward. As the wave moves through the slinky, some parts of the coil bunch together and other parts spread apart. These tightly packed area are called the compressions, and the spread out parts are called rarefactions. These are my compression zones. These are my rarefactions. Sound waves are an important example of compressional waves. Sound waves are produced when something vibrates, such as a speaker or a tuning fork. Those vibrations push nearby air molecules together and then allow them to spread apart again. This repeated pattern of compressions and refractions travels through the air as a sound wave. Sound can also travel through liquids and solids and is often much faster in denser material. Water waves. This slide shows water waves in more detail. Water waves actually involve a combination of motion. The water particles move up and down, and also slightly back and forth. Because of this, the overall motion of water particles is somewhat circular. If you place a floating object in the water, it will move in a circular path as a wave passes. This slide will discuss earthquakes and seismic waves. If you are very interested in learning about earthquakes, take earth science. Anyway, seismic waves are produced when energy is suddenly released inside the earth. These waves travel through the earth's crust and cause the ground to shake. Seismic waves are interesting because they include both transverse and compressional waves. In the diagram, it'll show different type of seismic waves moving through the layers of the earth. Chapter 10, Section 2, Wave Properties. In this section, we will examine the measurable characteristic of waves such as wavelength, frequency, amplitude, and wave speed. These properties will help scientists and us describe and compare different types of waves. Parts of a transverse wave. All right, this one's fun. Ready? At the top of a mountain, you're at the crest, right? And animals, they eat out of a trough. Wavelength is the amount of distance between two crests or two troughs, if I had one. And then the amplitude is measured from the increase of the crest or the trough. It can be measured in either way. All right, so if we instead are looking at a compressional wave, we'll see our compressions to compressions. That is another way of measuring our wavelength. Or we could do rarefaction to rarefaction. Either way, we're going to get a wavelength, just like in the previous slide. Frequency. This is one that we tend to get a little messed up, so let's make sure we all got this one. Frequency measures how many wavelengths pass a fixed point every second. And yes, it does need to be measured in seconds. The unit for frequency is hertz, abbreviated capital HZ. 1 hertz means one wave cycle passes that point every second. A wave cycle is from one starting point on a wave to the next starting point of that same region. So if I was reading it off of these amplitudes or these crests right here, this could be a passing point, and then where the next one starts, that is a wavelength. The diagram here compares the high frequency waves to low frequency waves. High frequency waves would be something like gamma radiation, where low frequency is something like radio waves. It'd actually be much further apart. All right, frequency again. So if we're looking at a measurement, a highly frequent, meaning it happens a lot of times per second, wave will have a higher frequency. So that's a frequency of 3. And then as we go up, we are descending in frequency. So we're getting slower waves, which means they have less energy also. But we will get to that part once we start analyzing these waves. A period is the amount of time it takes for one wavelength to pass in a set point. So not necessarily a second for that one. Period and frequency, we tend to get mixed up, but remember a frequency is going to be, for us, in seconds. A period can be uh, as much time as we want. Could be years, could be months, could be minutes, but it's whatever we decide. Frequency versus period. Here you'll see both of our different formulas we can use, either for periodic time or for frequency. You'll notice we have to determine what the periodic time is to know what period we're looking for. If we're saying a period is every 3 cycles, then we can put that in. If we want it longer, then we can have it longer. They are the inverse of each other. Frequency versus wavelength. This is another one that is very important to you in the class. We need to examine their relationship between each other. As frequency increases, wavelength decreases. We call that inversely proportional or inversely related. So if something has high frequency, you know that has short wavelengths because it has to pass that point more often. A low frequency will have long wavelengths. We will also talk about their energies. This top one, where we have short wavelengths and high frequency, will have more energy than a long, low frequency. All right, wave speed will depend on the medium that we're traveling through. Uh, we're going to measure it in meters per second, and we're going to use lambda, this letter over here. And it looks a little something like this. So you'll draw like that, and then you'll put a line through it. It's not perfect, but that's roughly how you should be drawing these. I find it is easier to draw the swoopy part first than the leg part, because if you start with the leg part, sometimes your spacing gets off and it looks a little wonky. So let's try this out. We are given a wavelength of 2.5 meters and a frequency of 170.5 hertz. So we are trying to find the wave speed. So that would be 170.5 times 2.5. You'll want a calculator for that. But if you get it, that does equal 426.25 meters per second. Oh, look at that. Amplitude. Amplitude is the measured amount of energy a wave carries. For transverse waves, amplitude is described as the height of the wave from a center line. It could also be the depth. Remember, we could measure that from either this amplitude or this one. Doesn't matter if it's center line to crest or center line to trough. It doesn't matter. The greater the amplitude, the more energy the wave carries. So if you think about it in terms of something like the ocean, we know that a big wave carries more energy than a ripple in the water. Amplitude for compressional waves is slightly different. Instead of measuring height, we measure how closely together compressions are. Stronger compressions indicate greater amplitude and more energy. In sound waves, higher amplitude corresponds to louder sound, so higher decibels. Section 3, Wave Behavior. In this section, we will examine how waves interact with objects and with each other. Examples include reflection, refraction, diffraction, and interference. Help me, I'm still stuck in the computer. Help me, please help me, someone help me. Reflection. We've all seen it. You probably look at your reflection once a day. Reflection occurs when a wave strikes an object and then bounces off. This behavior occurs with many types of waves, including sound, water, and light. The example we're going to use is a reflection. You can see the reflection of the mountain and the range behind it on the water below because it is non-moving and the light is bouncing off of it. Just like in a mirror, the waves are hitting the surface and being bounced back at an angle that we will understand later. Echo. Echo. Reflection also occurs when waves strike an object, like in sound. When sound waves hit an object and bounce back to your ears, you hear the sound again. Animals like bats and dolphins use echolocations to hunt objects and prey. This is called echolocation. Tanks, nope, not tanks. Submarines use echolocation called sonar to do the same thing on a computer to see different masses in the water. Refraction. Hey, who broke my really nice red straw? No one broke it. Me from a couple seconds ago. That's actually refraction. Refraction occurs when a wave bends and it changes the speed while moving because it goes from one medium to another. In the example up here, we are in air, which has a refractive index pretty low, almost nothing, to water, which has a refractive index. So the light is changing speed when it goes from going through air to water, so it makes things look like they're bent. The bending makes it look broken. If you've ever tried spear fishing, like this really cool guy in his gray shorts, you'll notice when you try to hit the fish, it is not typically where you think it would be, unless you are standing pretty close to the angle of incident or directly above the fish. If the guy was standing here, of course, he'd be able to just reach his hand in and grab the fish because he has really long arms. Diffraction. Diffraction occurs when waves bend around an obstacle. Instead of traveling in a straight line, the wave spreads out after encountering the object. The example is light bending around the edges of this ball. See, if you were sitting right here, it would look dark to you because the wave has bounced around you. Knowing the difference. So how can you tell the difference between reflection, diffraction, scattering, absorption, transmission? How do I know? Well, the thing you're going to want to look at first is you need to see when and why we are changing direction and if that has a change in speed. Diffraction is going to happen when we go around an object or an opening. Refraction is going to occur when we change our speed. Absorption is going to happen when something is the same color of something else. Uh, and we'll talk about that one more when we get to color. Uh, it's also going to involve reflection. And then scattering, something different entirely. Diffraction again. All right, so if I have waves that are trying to pass through a small opening, they will spread out on the other side. The smaller the opening to the wavelength, the more noticeable diffraction becomes. This is a bending of a wave. Interference. Interference occurs when two or more waves overlap. When they combine, they create a new wave pattern. However, this pattern only exists while the waves are still overlapping. You'll notice in this example, A and B come together to form a combined greater amplitude than both previously. If we added them up, if this was 1 and 1, this would be an amplitude of 2, but then as they separate, they go back to being 1 and 1. Constructive interference is like in that last example where when we put them together, the amplitudes add up. So you might be wondering, what happens if they aren't constructive? Well, guess what? Destructive interference is where two opposite waves overlap and they cancel each other's amplitudes. This is where we end up something with this nice center line like you see down here. They're both going in the same direction, but you'll notice amplitudes, crests and troughs are on opposite ends. So when they hit each other, they flatline. Standing waves. This is one that is sometimes harder to understand, and hopefully when we look at some examples in class, it'll come a little bit more obvious. But standing waves occur when two waves of the same frequency and amplitude travel in opposite directions and continuously interfere. This creates a wave pattern that appears to stay in one place. Standing waves often occur in vibrating strings like guitars or rubber bands. It will also become important when we talk about some engineering later on in the chapter. Resonance. If you are somebody who has ever used a tuning fork or played an instrument, you may be aware of resonance. Every object has a natural frequency at which it vibrates. When energy is added to the natural frequency, the object begins to vibrate strongly. If you've ever been in a house where something rattles or shakes when certain parts of a movie are playing through your speakers, even though they don't the whole time, that is because whatever the output of that speaker is at the same resonance frequency as that object. Every object has a resonance frequency. If you have ever seen someone use a strong note to break a glass, that is an example of resonance. That is not make believe, believe it or not. If the object absorbs enough energy at resonance, it can break it apart. Even small vibrations that are constant enough can cause this to happen in nature. Resonance. If enough resonance is added, even things like large structures and buildings and bridges can be destroyed. Uh, One of the rules, because of a different incident that we'll talk about later, happened because of humans not fully understanding frequency. Soldiers used to cross bridges at the same time and were marching in tandem, and that caused older bridges to break. And when soldiers arrive at bridges now, even with modern building technologies, soldiers are instructed to break stride. That is to prevent matching the natural frequency of the bridge or building and prevent destruction. All right, for this last one, we will watch this video. It is about the Tacoma Narrows Bridge, which collapsed in the 1940s due to resonance caused by wind. And yes, wind does also have a resonance. Uh, it'll show the oscillations, so the slight spinning it has before it eventually leads to failure. And that is one of those things that engineers now have to know to account for and didn't necessarily understand the ramifications of before. All right, thank you. I'm still trapped in the computer. Please help me. 6-7, Skibbity Toilet Riz. Please help me. 5 booms. Boom, boom, boom. Oh no!